Hello everyone, my name is Chang Huang from the Department of Applied Mathematics at the National University of Tainan in Taiwan. Today I'm gonna show you my recent work about some geometric results. The title is Purpose-Gooding Theory and Constant Mean Curvatures in the Flat Pseudo-Hermitian Manifolds. Actually, we consider the three-dimensional Heisenberg groups as a flat pseudo-Hermitian manifold. And the overview would be there are 4 parts in this talk. From the first one is the classic. We will review some classical purpose-gooding theory, and after that we will have some preliminary for three-dimensional Heisenberg group H1. And the third one is the main results. The last one is some topics related to the minima surfaces. All contents in this talk can be obtained from my previous result and which was published in 2017 and 2021. The last one is the second one is a generalization of the theory of purpose-gooding theory, and which was published in a journal of geometric analysis. The first part of the talk is a classical purpose-gooding theory. So that the theory states that there are 2 parts for the purpose theory, and the first part is one is for finding the surfaces, and the other is to find the volumes. And for the surfaces, we suppose there is a rod with length c, like as a blue line show, and when we rotate the blue line about a fixed axis with distance a is the distance of the center of the mass of the rod to the fixed axis. You rotate it, you get a surface of revolution, and the surface area is 2 pi times a and c, which is the perimeter of the circle times the length c here. And the similar results can be found for the cones and even for the spheres. So let's write in detail that there are 2 parts. The first one is the surface area. It says that the surface of revolution sigma generated by rotating a plane curve C0 about a fixed axis which does not meet C0 has the surface area like this, and whereas S0 is the perimeter of the circle described by the centroid of C during the rotation. The other one I call it theory B. We calculate the volume of the solid of the revolution M, which is generated by rotating a region R about a line L, which does not meet R itself, and has the volume as follows, which the volume equals the area of the region times the perimeter of the circle described by the centroid of R during a rotation. Okay, those 2 results are quite standard, and I believe you can find the result in the textbook of calculus. And there are some background review related to the topic. 2 good men, the 2 mathematicians are good men. A.W. Goodman and G. Goodman generated the theory B, which is a volume part of the purpose-gooding theory. It says that if the region is around an arbitrary space curve, then the center of mass of R, when the center of the mass of R is on the region is on the curve, we have the volume formula. The volume is equal to the area times the length. However, the author also showed that the surface result for purpose-gooding theory does not hold in general, It only holds for the surface area of sigma generated by moving a plane curve around a plane curve around a plane curve gamma with some natural motion. Okay, I will explain this later on. Okay, and after that, two mathematicians, Flanders and Purcell, independently supplemented the result of the surface areas in their result by showing that there exists a unique spin function such that the area of the surface generated by C0, the result still holds for the theory, the volume part. So say the area part. The area is equal to the length times the length of gamma. It's like previous results. In 2000, Gray and McGill generalized for volumes and surface area to the hypersurface in space forms. Okay, so my first question is that the motivation why Pappas-Gooding theory. Actually, Hermann Weyl proved the famous of the volume, the formulas of the volumes of the tube, PR. PR means the tube with radius r, and the corresponding tubular neighborhood hypersurfaces, the boundary around a q-dimensional submanifold P in a Euclidean or spherical space. And finally, those formulas were used later in the proof of the generalized Gauss-Bonnet theory by Fenchel and Alexander. And the survey, for more details about the Pappas theory, the reader can refer to the Bangkok, is it? The pronunciation, for more details about the connection of Weyl's work and the theory. The question of the study is as follows: does Pappas-Gooding theory still hold in the three-dimensional Heisenberg group? We call it H1. And what are the appropriate geometric quantities, for example, like length, surfaces, surface areas, volumes, satisfying the geometry of Heisenberg groups as a standard model of the sub-Riemannian manifold or pseudo-Hermitian manifold? The answer is affirmative if we take the following geometric quantities. If we take the horizontal length for curves, we take P area for surface areas, and take Euclidean volumes for solid domain in H1. We will show the generalization of Pappas-Gooding theory for volumes and surfaces of any tube consisting of a plane region moving along a curve, any curve, not just a planary curve. It could be a spatial curve in a three-dimensional Euclidean space. Actually, I will explain this more later on. Okay, here is this one. Okay, here is how we construct the tube in R3. Okay, so give us C3 regularity closed curve in R3 and the Frenet T and B. Okay, you can see the picture here, and this is the spatial curve, and we start from this point R0, and we have the closed curve, say capital R, and we start from the point and we move the points, and we have a plane region R here on the line on the XY plane. When you move the plane, we keep because the plane region R is on the XY plane, so the normal vector is perpendicular to the XY plane. When we move the region R perpendicular to the curve, it means that the tangent of the tangent T of the curve is always the normal direction to the region. Like this, when you move around over here, we have the other tangent. The tangent T is the tangent of the curve R, and also the normal of the plane region. Okay, and now we define the curve we say is C0. C0 is an arbitrary curve, and at the beginning it is on the XY plane. Okay, and now we have a tube like this. Now you have a tube. When you move around the plane region, you have to keep the tangent vector as the normal vector of the plane region, like this. The natural motion means that the surface sigma generated by moving a plane is always perpendicular, as I mentioned before. Okay, this is a so-called natural motion. Okay, the tangent of the curve is the normal of the planary region. Okay, when you move here, then we got a new region, plane region, and the tangent of the curve is still the normal of the plane region. Okay, so let's recall some preliminary for the three-dimensional Heisenberg group H1. The three-dimensional Heisenberg group is a Lie group R3 with a group operation defined as follows. The first two components of the points in R3, you just add them together directly. For the third one, we have the twist term, which is z plus z bar, and this is a twisted term. Okay, and in H, so you okay, so and for any points in Heisenberg group H1, the left translation by P is the diffeomorphism defined from the left. So the operation here is defined as before up here. The standard basis of the left invariant vector field is defined by the standard Euclidean basis, but the only difference is there is the function in front of the z direction, and for the z is just a z, the usual axis of the Euclidean space. But for the other two cases, E10 and E20, there are two functions y and minus x in front of the third coordinates. Then the standard contact form is the dz plus x dy minus y dx, and the contact plane is spanned by these two standard bases, E10 and E20, this one and this one. And here we use a Levy metric. We use it's the contact form with some vectors in H1, and such that the E10, E20, and T actually is the third component of the Euclidean in a Euclidean space, which is just z direction. It's an orthonormal basis in the Lie algebra of H1. The standard CR structure is an endomorphism J, defined in the whole space such that JE1 just rotated by 90 degree, E1 to E2 and E2 to minus E1, 0. And for the T direction, it vanishes. And J square is equal to -1, which is an almost complex structure on the contact plane. Okay, so just remember that the contact plane sigma c is spanned by E1 and E2. Here is the electron. I will illustrate the contact planes in Heisenberg group. So here each plane is spanned by E10, and E20, depending on the points P. P is here, P is here. Different points we have a different contact plane. Okay, spanned by these two. And here, this is a curve. We call it horizontal curve. Means that for any curve in R3, if the tangent vector at each point is contained in the contact plane, C, contact plane. Okay, so such a curve is very special because the tangent is always contained in the contact plane of the space in H1. Okay, and we in this geometry there are several interesting things. We call it horizontal or Lagrange geodesics. In this case, in H1 is helix and horizontal lines. Horizontal line means it's just a line, but the tangent at each point on the line has to be on the contact plane, passing through the given point. And the PSH is the group of the pseudo-Hermitian transformation in H1. Defined as follows. For the group is a set of all diffeomorphism from H1 to H1 satisfying the almost complex structure can be commute with the diffeomorphism, and also has to preserve the contact form. In 2017, Chang Huang, Lai Xinhua, my co-authors, and I, we proved the following theory that any elements in a pseudo-Hermitian group must be the form of the left translation, and we call it rotation. A rotation in a one-dimensional unitary group, and a left translation LP. So, and there is a natural decomposition of a regular curve. For a regular curve, this is a tangent, the Euclidean tangent of the curve, and Euclidean tangent of the curve, and it can be decomposed into two parts. One is on the contact plane. The other is along the t direction, which is the partial z. Alright. And because we know that t and the contact plane is perpendicular to each other, so we have the orthogonal decomposition, and with respect to the Levy metric. And we prove that any horizontal regular curve can be uniquely reparametrized by horizontal arc length S up to a constant such that the length is equal to 1. The result is quite similar to that in the Euclidean space. So you can always reparametrize any regular curve in Euclidean space such that it is a arc length parameter. And a curve is horizontal, is defined as follows: if its tangent at any point on the contact is on the contact plane. So if you really calculate, you have the result like this. Here gamma s is written as the x, y, z are the components of the curve. So if gamma is horizontal, then the components satisfy the result, the rule like this. And there are two geometric invariants we got in our previous work. One is called P curvature, and the other is called contact normality. The P curvature is defined as the second derivative of gamma. Here's and make the inner product with the tangent, and we put the applied by the j. So j means that we just rotate the curve, the vector by 90° on the contact plane. If we have a contact plane, and any vector on the contact plane can be spanned by the standard basis E1 and E2, 0. So we apply J, means that we just rotate this on the contact plane by 90°. Okay. And this is an invariant. Under the pseudo-Hermitian transformation, we prove. And the second geometric invariant is called the contact normality, which measures the how far the tangent away from the z direction. T means the z direction, right? So we have a t here, and we have a curve, and the tangent of the curve. If gamma is on the contact, if gamma is a horizontal, then it means that the tangent is on the contact plane, right? So if tau is 0, if and only if gamma perpendicular to t. So if and only if gamma is on the contact plane. Okay, so gamma is horizontal by definition. So the tau, so that's why we call it contact normality. It measures how far the measures if it's a horizontal curve. Okay. So the kappa is analogous to the curvature of the curve in the Euclidean space R3, because here is a second derivative of the curve. The only difference is that it does not it doesn't make inner product with itself. It just with the other one. And tau measures how far the curve is from being horizontal. A curve is horizontal if and only if tau is equal to 0. And if the curve is not parametrized by arc length, it's just parametrized by arbitrary parameter u, then we prove that actually we have the two formulas for the curvature and the contact normality. And we also prove the net frame formula for any horizontally regular curve parameterized by horizontal arc length, which is given by the following theory. So although the Heisenberg group H1 is equivalent to R3, but you can tell from here the formula is very different, because we have the z direction part. Okay, they have different geometry in the Heisenberg group and R3, totally different. And because the t direction is always pointed for upward, so it does not change by the parameter s, so the derivative is always 0. So we prove the fundamental theory for curves in H1. It states that given a smooth function kappa and tau, there exists a horizontal regular curve gamma such that first s is a horizontal arc length. Secondly, the function must be the peak curvature, and the tau is the contact normality. This is quite we call it, it's a like prescribed curvature problem. Given two functions, can you find a curve satisfied such that the functions are just the curvature of the curve, of the given curve. And we also proved that given two curves, gamma and the gamma tilde, if their geometric quantities kappa and tau are same, then those two curves must be same and up to exactly same up to a translation, up to a pseudo-Hermitian translation. So this is a very just analogous result to the theory in the Euclidean space. And we need more backgrounds about the surfaces in H1 for our purpose, because we have to figure out the Pappas-Gooding theory. We need a volume, we need the surface areas, we need the length. So that's why I spend some time to recall some fundamental results for length. And now let's move on the surfaces. So a point P is singular if on the surface in H1 if the tangent space is equal to the contact plane at P. So it's like this. We have a surface here, sigma, and any point here, and actually we have a tangent plane through the point P, but also at this point we also have a contact plane depending on the point P. So this is a contact plane at P. Okay, so if they coincide to each other, we call the point singular. Otherwise, it's non-singular. So actually, you can, if they are non-singular, there must be a one-dimensional intersection between the tangent space and the contact plane. Okay, so the intersection defines a one-dimensional foliation. So we choose a unit vector E1 in the intersection, and there is a unique vector E2 perpendicular to E1 also on the contact plane. So like this, we have a contact plane at non-singular points, and we have the other tangent plane at P, and there's a one-dimensional foliation, so we can have a vector E1 on the foliation, and we can find the unique up to a sign. Okay, you can have a JE1. Just rotate the vector E1 on the contact plane by 90 degrees. This is E2, which is E2. So E1 and E2 perpendicular to each other with respect to the Levy metric. We call it P normal of the surface. So suppose the surface bounds a domain M in H1. We can define a P area 2 form by computing the first variation away from the singular set, the singular points of the standard volume in the P normal E2. Okay, so we just make the variation along the normal direction. Then we have P normal. Here is a volume, right? It's a volume. We make a variation on the volume. Then we will obtain the surface two-dimensional two form, and where f is a smooth function on the surface with compact support away from the singular points. Okay, the C2 is the normalization constant. The sign of E2 is determined by requiring that the P area form is positive with respect to the induced rotation on the surface from the Heisenberg group. And Chang Huang, they derive the formula for P areas for any hypersurface in a higher dimensional Heisenberg groups. And in particular, when n equals 1, it's a graph type. Now, the graph type sigma, the surface area of the graph type surface can be obtained by the formula here. And the P area form can be continuously extended over the whole surface sigma by having the p area form vanished and the set of singular points. So we conclude that the p area form is completely defined in the whole surface, no matter its singular points or non-singular points. The p area of the sigma is also coincide with the 2n plus 1 dimensional spherical Hausdorff measure of the surface. Okay, we refer the reader to the paper here by Chang Huang and Yang. And next we are gonna recall the volume and the area forms in the relation between them. The volume of the domain is nothing but the three-dimensional Lebesgue volume, just a regular Euclidean volume. And if we have, as we mentioned before, if we make a first variation along the normal direction, we can have the p area. So the p area actually is defined to be the contact form, which times the E1, which E1 actually is the dual. E1 is the dual of the E1. This E1 is a unit vector on the one-dimensional foliation, which is the intersection of the contact plane and the tangent plane. Okay, and the p area form is globally defined on the boundary of the domain and vanish at the singular points. And they also define the Chang Huang and Yang. They also define the p mean curvature by making the variation along the normal direction on the p area form, and this time they get the h here, which is called the p mean curvature. Several equivalent definitions for volumes and surface areas are also studied by the following mathematicians, and including all mathematicians here. And also Chang Huang and Marcuati Yang study the structure of singular sets, p area, constant p curvature surfaces, and they have several results. For example, they prove that if the p mean curvature h is bounded, the singular set consists of only isolated points and smooth curve. So this is very useful because if it means that if the assumption holds, then the singular set is just measure 0 if we want to if we take the p area as a measure, because it's just that set of isolated points and smooth curves. And suppose sigma is closed and connected umbilic hypersurface in Hn for n is greater than or equal to 2 with positive p mean curvature, constant p mean curvature, with and non-vanishing Euler number. Then the surface is congruent to the Pensu sphere. Pensu sphere is a model and also the sharp case of the following conjecture. There is we call it an isoperimetric inequality. Inequality is an inequality, and the conjecture states that if the equality holds, and the surface must be a Pensu sphere. As I know, the result is still open. So, okay. But Pensu sphere is kind of important in this geometry. Okay, so in H1 now, come back to the Papa-Gooding theory. In H1, we consider a more generalized surface like this. If we write the curve gamma s, and this is gamma s, and at each point we have u, v, and t. What is u, v, and t? U actually is the horizontal tangent. It's a we make a decomposition of the tangent vector, and this is the part on the contact plane, and this is the vector by rotating the previous one u by 90 degrees, so it's still on the contact plane. So now we have u, v, both are on the contact plane, and t is just the normal direction. So I put the very general functions f, g, and h. Okay, so now we have a curve gamma, and we use the generalized surface, and to see when the Pappas-Gooding theory holds, and for if we have to put some conditions on the functions f, g, and h. Okay, and I point out that the u, v, and t forms an orthonormal basis with respect to the Levy metric. An alternative perspective for the equation 1. Consider H1 as a D group. The surface sigma can be obtained by moving the frame at the beginning when s equal to 0 at the origin and along the curve gamma. So you can have that, because the sigma like this is a tube. It's a tube. So we can have like when s equal to 0, this x 0, 0. Sorry. When s is equal to 0, s equal to 0, t. Okay, and we have some curve, some closed curve, and you can regard the surface as the one translated by the left translation. So remember, this is a left translation applied on the point here by gamma s. So actually the tube can be regarded as a lot of layers, and you just copy the first one to the second layer, and copy the second layer to the third one, and so on. And it can be proved that those two surfaces, 1 and 1 prime, define the same one. Okay. And the surface of revolution sigma is defined by rotating the closed space curve, which is spanned by the u, v, and t. Okay, along the curve. This is what I meant. Okay, and next I'm gonna show you my main results. Okay, so basic assumption are those 3 points. The first one is the closed curve CST, which is like this, CST, and this is a curve gamma S. Okay, does not intersect itself when moving along the curve. And the second one is the domain enclosed by the parametrized surface defined in the previous one is not self-intersected. Okay, so and the minimal regularity for the sigma is C2. And here is the first proposition. Given the parametrized surface and the P area form at the non-singular points can be represented in the following term. It's like this, where A and B are can be calculated as this one. This is a partial derivative with respect to the parameters s and t respectively. The P area of the surface sigma is given by the integral of the P area over all points on the surfaces and which is actually, if you write in parameters, we have the square root of a squared plus b. Okay. And actually, the coefficient a, b defined above can be represented in terms of the inner product of the standard basis and the vector here with respect to the Levy metric, like this. And we define, because the reason I have to show the lemma here, because actually when you deal with the a and b is quite complicated for the calculation. As I mentioned before here, you see there are several terms in a and b, so it's very, in general, it's not quite easy to calculate this one when we want to find some examples. So that's why I have some much more geometric interpretation for a and b. Actually, this is the cross product. I define it on the basically we follow the same rule as that in the Euclidean space, but the cross product we regard the orthogonal basis by E1, E2, 0, and T. So we just use these three as a orthonormal basis, and we keep the same rule as that from the Euclidean space. Okay, but we change the basis. So that's the projection of the like normal I quote the normal direction along the projection of the normal direction on the E2 vector and to the E1 vector. Okay, when the first question is that when P area equals R2 area, and our example shows that the vertical plane, which means a perpendicular plane, it's a plane perpendicular to the xy plane. So any plane like this, like this, here is a x and y and z. Any plane like this perpendicular to the xy plane, and it has the same P area and the Euclidean area. Okay, this is the first example we show in our paper. And how about graph? The graph like ST and FST for some function FST, and in general it's not equal, because if I really calculate it, the P area is as follows, but which is different from the Euclidean surface area for the graph X. So they are different in general. And next, we ask that the Papa theory for volumes holds in H1 when the domain is obtained by parallel moving a plane region along a line on the xy plane. The reason is that because as we mentioned in the previous slides, when the plane is perpendicular to the x and y plane, the P area is equal to the Euclidean R2 area. So the R2 purpose Gooding theory for volumes can completely applied in this case, because they are same, right? So, and also the volume in R3 is nothing but the volume in H1. As long as we know the P area, as long as we know the P area of the P area in H1 is equal to Euclidean R2 area, then we can apply the Euclidean version, the theory of the Euclidean version, then you just get the result. The special
I'm sorry, I didn't quite catch that.
So the special case for purpose Gooding theory in H1 states that when the line segments with horizontal length S0 on the xy plane, in this case the region is just perpendicular to the x and y plane, as I mentioned before. So It's kind of like a special case. And next, given a domain M with boundary partial M, and that E1, E2T be an orthonormal frame with respect to the Levy metric, and such that E1 is in a one-dimensional foliation and E2 is as before, and we denote the dual basis, which is three one forms, E1, E2, and contact form, and we have the following diverse theory. Okay, so the diverse theory, if any vector field vector value function P defined by P1 E1, P2 E2 plus P3 T, and we have the following divergence theory. So it means that the subdivergence of the vector valued function, the integral is equal to the double integral on the surface of P2 for the P area. Okay, okay. So we got the formula, the transformation rule from the volume to the surface. So we have the following corollary, and says if let M be a domain in H1 with boundary, then the volume of M is given by 1/2 of the double integral over the boundary. Okay, and if the boundary is parametrized by the surface, actually we have the results. The volume can be represented by the following things, and here A and B is just the two ugly terms as we mentioned before. Okay, and we point out that the coefficient in front of the double integral actually is very similar to the case from the Euclidean space. As the next results, see similar to the result in R3 when we apply in the divergence theory to the position vector P of a closed parametrized surface. The volume of the enclosed domain here is in R3, right? And is equal to 1/3 of the triple integral. Okay, and that's the results comparing with that in R3 case. And we also show several examples, like by the formula we just derive here. We use the formula here. We derive the volume to calculate some concrete example. Because we have already know the volume in H1 is nothing but the volume of R3. So they should be same. So it's just like examination. So we show that the solid torus, the volume of a solid torus, and we can write the parametrization for the torus, and we calculate A and B actually, and by the previous rule it's okay, it makes sense. We just check that if our derivation is correct or not. It is one of the examples. Okay, so now we have an immediate application. It's an isometric type inequality for the domain M with boundary partial M. By the Cauchy-Schwarz inequality here, we can have the ratio of volume and the surface area, which is bounded by 1/2 of this one, and we observe that the left hand side, because they are nothing but the ratio of volume and the surface area, so it is invariant under the pseudo-Hermitian transformation. So it means that no matter where you move the ratio, where you move the domain M in H1, because the right hand side, take a look at the right hand side, this is just the distance, the distance to the z direction, z axis, right? Here's x, y, z, x, y, z, and this is a distance to the z direction. So it means that if you just move far away from, if you move far away from the z direction, this becomes very, very big. Okay, but how about if you move m including the z direction? So the ratio must be controlled by the maxima of the point, maxima of the distance of the point to the z direction. Okay, and here is a corollary. If we put for any domain M with boundary, there holds an isoperimetric type inequality. It means that the ratio of the volume is dominated by the inf and the sup. We move all G is just nothing. It's analogous to the rotation and the translation in Euclidean space. But here is in a pseudo Hermitian manifold H1. So we got the control of the ratio. Okay, so here is our main result. First one. Okay, suppose M is a domain in H1 with boundary described by the generalized parametrized surface as before. So we can have the volume. We just use the previous one. We calculate this. We put everything in terms of F, G, and H. It's the most generalized case. So we have the derivative of F, G, and H, and this is a volume form because we have already had the formula for volume of M. And okay, I think I skipped these slides. Okay, and we are asking when the volume is equal to the P area times the horizontal length of gamma. Okay, so now we have a tube, right? By the previous result, we know the volume of the tube, and we also have the formula for the P area, and we also have the formula for the length gamma. So let's check if, okay, my idea is the proof actually is simple, just based on the previous results. I've checked that because I have already had the three things. We have the volume, we have the horizontal length, we have the P area. Okay, so we just substitute the surface and calculate those three things: volume, length, and P area, and to see when they are equal to each other. Okay, to when the identity holds. Okay, and I choose and I would choose some appropriate G and H. Okay, so and actually satisfying the assumption A1 and A2. So what is A1 and A2? Let's check it. Okay. Oops. Okay, I forgot to put the A1 and A2 in the slides. Okay. I think you can check the paper if you like it. Okay. So the next one is the main results. Okay. Given a horizontal regular curve, it's a purpose good in theory for the surface. So we have to it's a similar idea is that we calculate the P area in terms of F, G, and H. Okay, and with some curvature condition. Okay, then we have this one, and next we should check when the area equals the length times the rod length at the beginning I mentioned. So but now in this case the situation is much more complicated because I have to deal with the curvature condition when torsion the contact normality is equivalently to equal to 1 or okay, we have this one, and we also have the other case. Okay, so there are two cases that the Papas-Gooding theory hold. Okay, like this and this. And I also shows two examples satisfy condition 1 and 2 in the corollary respectively. So the first one is a circle on the xy plane center at the origin, and the other one is the curve which is a helix. And here is here are two pictures as on if I show you like this is a gamma, and this is a closed curve rotate about the axis z axis, and also here this is a helix fixed, and there is a closed circle rotate about the z direction and to move to make the tube like this. Okay, and final example. Okay, here is the other example. We plan to find some gamma, and the gamma looks like this, and the curvature, we want to find some example with curvature 0, with 0 curvature, and the contact normality is 1, so to satisfy the assumption of the Papas-Gooding theory for surfaces case. And actually we just got these results, and the visualization is illustrated as follows. So we have the gamma as a blue line show, and we have the black curve, but it's not close. So we just move we just move along the curve gamma. We have the surfaces. And the last one is the related topic to the minimal surfaces. We ask a question: is it possible that the surface sigma satisfies the Papas-Gooding theory, and also which is a minimal surface? Okay, so we ask when the surface is a minimal surface. The answer is yes. By Cho, Lai, and myself, the previous result, we know that given any regular surface, sigma defined by gamma plus the tangent, the normal, horizontal tangent and horizontal normal, we can find the coordinates called the normal coordinates such that the parametric equation of the surface satisfies the following three conditions. The first one is the surface without singular point, so we can have the result like this. And the direction, the partial derivative along the s direction defines the character foliation, the one-dimensional foliation on the image. Okay, and also the surface is the curve. Those curve, integral curve is parametrized by our horizontal arc length. And in this case, the P mean curvature can be represented by the function h, satisfying the pseudo-Hermitian connection E1, E2. H actually is the like weighted function in front of the normal, the P normal vector. When using the normal coordinates, we can get the result for the we can get the formula for the P mean curvature, which is the second partial derivative of the surface along the t direction, and we dot with the j applied on xt. So we can really calculate the P mean curvature if we have the parameterized surface like this. So we really calculate this, the first derivative along t and double t. So by the previous result, we have this one. We can calculate the P mean curvature in terms of the coefficient in front of tangent, horizontal tangent, and horizontal normal. Okay, so now we need a minima surface. It means that the P mean curvature has to be zero. Has to be constant P mean curvature. Okay, constant P mean curvature. So we need this one as a constant. So we need to add the extra condition for this one. So now we can construct the P mean constant P mean curvature satisfying the Pappas-Gooding theory. So the corollary like this: when h is equal to 0, means that what is h? Just the surface is equal to gamma plus fu g v. Originally we have h plus t, right? T is the z direction, but now assume h is equal to 0 for any function ft kappa p curvature and the contact normality satisfying the condition like this with the P mean curvature constant. Then the surface defined by this guy is a constant P mean curvature as a surface, and also when we have some curvature condition tau equal to 1, we have Pappas-Gooding theory just based on the previous results plus some extra condition here for the constant P mean curvature. So finally we put some remark. We say that if the surface sigma defined above is a P minima surface, okay, minima surface means h equal to 0, it does not bound any solid region. Actually, when the condition for being a P minima surface is that h equal to this guy has to be 0, but this guy the identity holds if and only if there's a relation between f and g for some constant. Thus, it degenerates to a line segment such that the surface cannot bound any domain. So it's like a degenerate case. The result has been observed by the previous mathematicians Chang Huang, McCurdy, and Yang. They show that the P minima surfaces are classical ruled surface with the rule generated by Lagrange lines, and the rule surface does not enclose any bounded region. Okay, so I think I stop my talk here, and here just some basic introduction, and any comments and suggestions are all welcome. Thank you.